So my name is Nicolas Pitre. I've been working at Linaro for quite a while, since the beginning. I'm now part of the member of the CTO office. And for the best part of the last year or so, I've been working on looking at ways to reduce the Linux kernel for IoT purposes. So, as many of you might know, I am blind, so I don't see you. If you have questions, please interrupt me. Don't raise your hand. It might not be efficient. So this presentation is a follow-up, a sequel of what I've presented before. This is the result of my latest findings that I want to show to you. So, slide number 3, please. IoT. Of course, we want to have devices that are ubiquitous and cost-effective. They need to be reliable and usable, and they need to be secure. Most of the time, you cannot have all of those goals together. You have to pick two. Obviously, we want to have all them. So, slide 4, the solution. We need to reduce costs by avoiding custom software. So if we can reuse base software that people are relying on, that's what Linaro is all about, to reduce fragmentation and have common base. Leveraging open source software, of course, and getting a critical mass around a solution. And then the vendors can spend more time on what differentiates them between each other. So, slide number 5. I'm going quickly over those slides because I already presented those before. We know that Linux is a good solution because it has a lot of developers. There's a large knowledge base around Linux. It probably has the best networking stack available because there's a lot of people looking after it. Lots of storage options. Of course, with IoT, maybe it's not as relevant for servers, but still, if you want to have file system support, for example, it's already there. And Linux is already widely used into embedded systems for routers or devices which are not necessarily tiny, but still small. Slide number 6, please. Linux is cool, but it has drawbacks as well. It has a lot of features. Those features are mostly tunes for high-end servers and large machines. Usually, it's been optimized to scale up instead of scaling down most of the time. The configuration system is quite extensive, but sometimes it might be hard to choose the right configuration to have the best optimized kernel for your application. Okay, slide number 7, please. One other thing I've been looking so far are automatic ways to reduce the kernel, so we don't have to go left and right and trying to cut things manually. So one of the techniques is the linker garbage collection coupled with the GCC function section. And there's also the LTO, which is link time optimization. Slide 8, please. So, what is LTO? LTO is a really cool trick that has been implemented in GCC that allows the compiler to simply parse the C file and store its internal representation into the object file. And that's all. At the very final link, the compiler will gather all those objects file together, and then go through all its optimization passes, like if it was only one C file. The advantage of this is if, for example, you have a global variable, which is normally kept as a variable because the compiler has no visibility across different C files. Now, if the variable is set only at one place, then the compiler may assume that it's a constant and optimize everything around that fact. So if, for example, some functions are never called because the variable won't be set to the right condition, the compiler may just optimize all that code away, even if it's originally from a different C file. So this is really, really effective at removing unused code. Slide 9, please. LTO is cool, but one of its drawbacks is the build time. So here I have a table of a build test that I did. So if we take one particular configuration for the kernel, on my test machine, without LTO, it's about a little less than 5 minutes. With LTO, it's double of the time. It's more than 10 minutes. And probably the worst drawback is that if you do a single change in the kernel, for example, you just want to add a new line in a print key string, that single change will require a recompile of about 8 minutes instead of 12 seconds. So obviously, for certain circumstances, LTO might not be the right thing, especially if you're doing your debugging, you test something, it crashes, you recompile all the time. That's something I do. Move a print key around. Probably LTO will just get in the way in that case. Slide 10, please. So the alternative to LTO would be the what I call the poor man's LTO, which is the GCC function section. What it does is to assign a different elf section to every function. So in the example here, function foo would get .text.foo, function bar would get .text.bar, and same thing for the main function. Slide 11, please. Now, what the linker does is to garbage collect every section which is not referenced. So in the example here, if we build the code that we had before, we can see that text.bar section is gone because it has no reference to it. Now, if we apply this to the kernel, slide 12, please. So I used a hacked version of the kernel to compare the effectiveness of those solutions. So if we start with my base kernel, which is the all no config, the baseline would be 100% because that's my starting point. If I stub out all the system calls, in theory, there's a bunch of code which are not referenced anymore. Without any of those reduction techniques, the kernel will shrink to 94% of its original size. If we bring LTO into the picture, it's down to 56% of the original size. But if we see here, with the garbage collecting the function section and so on, it's a little bit less effective, 64%, but the advantage is the build time. So probably what we want is to support both in the kernel, having both options. If we can develop with GC section and then having the final build using LTO, and having both might also help if there is a regression and LTO support or things like that. Okay. Slide 13, please. Now, the problem is we have this nice tool that is supposed to remove all the code which is not referenced. Why the hell is there still 480 Ks of kernel code when everything has been configured out? It's something what I call anchors. Slide 14, please. There are many anchors in the kernel. Those are points where we enforce a reference to some code. For example, all the init calls in the linker file, even if we do LTO or GC sections, we have to tell the linker those entry points are being referenced somewhere. Even though they're not explicitly referenced, we gather them into a table. The linker might not see any direct reference to them, so we have to explicitly tell the linker, all the init calls, don't give them away. I want to execute them. Okay. If we look at how many init calls we might have, slide 15, please. So you see how it's easy to find how many init calls we can have. Here, I'm still talking about my all-no config kernel. It has 49 init calls. I'm sure that for a kernel, which is still supposed to do nothing since everything has been configured out, having 49 init calls is probably a bit high, especially since most of them are there to probe things, set up things that we're probably not going to use. Okay, other examples, slide 16. All the early param parsers are using the same technique. They're gathered into a table, and we have to tell the linker, don't get rid of them, because we don't know. We might be able to parse things from the command line or from module parameters. So those are being gathered in the kernel, even though we might not use them. So again, we have, for example, 47 entries of one kind and 12 other entries here. There's probably something we can do about those things. If we are talking about IoT, I would be surprised if users will be asked to change their kernel command line, right? So probably we could, during the build of the kernel, parse the command line that we want to pass to the kernel and hard code those parameters in the kernel at some point. Okay, slide 17. Another source of anchors, export symbols. Last Connect, I did a presentation, extensive, I talked extensively about those export symbols because they are all over the place. If you do want support for modules in your kernel, you have export symbols everywhere. So the idea is to be able to remove some or most of the export symbols that you're not going to use. If you have only a handful set of modules, I doubt that you will require the thousands of export symbols that you have in your kernel. And yet, those symbols are the export symbol statement is there to tell the linker, don't get rid of that function, because sometimes maybe a module will want to link against this. So, what I sent upstream in Linux 4.7, there's a new configure options that allows you to tell the build system, I want only those export symbols that my modules require. And afterwards, LTO or GC section can get rid of all the functions that are normally exported to symbols but are not required for your module set. So slide 18, please. Here's an example of a small configuration, kernel configuration that I used to illustrate this. Before the patch, not the patch, but this function was enabled, we have more than 5,000 symbols being exported. With the set of modules being configured in, only 52 symbols were required. And you can see the reduction of the kernel. This made a 13.6% reduction of the kernel. Which is nice here is if I disabled module support entirely, then the kernel will shrink by 13.9%. That means with this, the overhead of module support went from 13% of the kernel to 0.3% of the kernel. Now, one might ask, why would I use modules with IoT purposes? Let's say you have very, very small amount of memory and you want to do firmware update. Maybe at that point you will require flash write support, so that can be done into a module that you won't need otherwise, and when you're in normal operation, you might have another modules to do other operation in your device. So it's a bit like what we call overlays in ancient times when we used DOS and those systems with very small amount of memory. I'm giving away my age here, I think. Okay, slide 19. At some point, automatic reduction might not do the trick. We need to have subsystem specific trimming. Some example of things that have been done already, we can already remove the block subsystem entirely. We can remove NTP support. We can remove capabilities from the kernel. We can remove user support from the kernel. So everything is run as root. And that's probably typical of the small embedded systems. Everything is run as root. So why carry the support for user permissions and group and so on? We can remove PRNK from the kernel. Eventually, if you want to fit your application into a tiny device, it probably won't have any way to output strings to the user. So why just remove PRNK support? So we need more options like this. Slide 20, please. What to look for? Here is an example with my tiny config. We can look at the size of the object files from subsystems. So I've sorted them out here. So you have a list of the size of some subsystem. Here, keep in mind that we're still talking about the tiny config kernel, which is very close to all no config kernel. So there's a lot of code here that no one ever bothered to configure out. Slide 21, please. So I picked one at random. Let's look at the time subsystem. POSIX timers. There's a huge amount of code to support POSIX timers. and especially one type of timer, which is the POSIX CPU clock timer. Removing that, we still can keep the basic function of the timers, the most used one. For example, the real-time and the monotonic clocks can be preserved with very little code. Slide 22. That allowed me to save 12 kilobytes of kernel memory. And the nice thing about this is that standard distributions still boot on that kernel. Surprisingly, not many things uses POSIX timers. But no one until now bothered to make them optional. Okay. Slide 23. So, we can ask ourselves, if in the all-no kernel, print K is removed, why have we still 2.5 kilobytes of printing code? That's probably an easy one. Slide 24. We still have 4 kilobytes of locking code. This is a single processor. It's not SMP. In theory, a lot of the locking code should just go away. Probably there are some SMP remnants in there. Slide 25. Now, 18 kilobytes for interrupt support. I don't think that we need that much code in some embedded systems. Most of the time, we have 4, 5, 6 interrupt lines. They are statically assigned. We know how they behave. Most of the time, it's really directly connected to the CPU. I really doubt that we need 18 kilobytes of IRQ infrastructure to support this, right? Slide 26. Now, all the drivers have been configured out. Why the hell is there still 75 kilobytes of driver code? Slide 27. 80 kilobytes of memory management. This is a no MMU configuration. So in theory, memory management should be very trivial. Slide 28. And we're in Vegas. So here's the jackpot. All the file system have been configured out. Why do we still have 110 kilobytes of file system support code? So all those things really add. They add up for things in theory, and if we think of a very, very strictly controlled embedded system for IoT, for example, with very low memory, all those things are most likely not going to be used. So, slide 29. Trimming those things away won't cut it all the time. We might have to look for substitutions. For example, we already have 3 memory allocators. Slabs, slub, and slob. The slob, S-L-O-B, allocator is there. Its purpose is to be very simple, with very little code, and to be small. So this is most appropriate for embedded systems, and I'm sure it's already used in those circumstances. Now, it's probably the time that I must be the most daring. Slide 30. Yeah, right. What about the scheduler? Should I go away now? This is a very controversial topic. Many people tried before to suggest that we have pluggable schedulers or alternate schedulers and so on. So why not get in that pool of people and get flame and so on? So I tried it. Let's have some fun. Slide 31. Let's look at the existing scheduler. It has close to 30,000 lines. It uses 140 kilobytes of memory. That's a lot, especially if we are talking about an embedded system. So, of course, to be fair, that amount of memory is with a standard configuration. It's not the tiny configuration, but it's just to illustrate that the current scheduler is quite complex. So this is clearly not for small systems. So, slide 32. Let's try to make the slob of scheduler. So my goals were to have the smallest code base possible. No frills. I don't want to have any configuration in the scheduler. Let's keep in mind this is for an IoT device. It probably have to schedule one task, maybe 2, 3, 4 threads, and that's all. So let's dispense with SMP support and have simplistic scheduling policies. No user interface, I said minimal, but I tried to remove all of them. And the idea is to still have a scheduler which is correct with regard to its behavior. So I still wanted to have something that can run the standard kernel and standard distribution, although it won't scale as much, but at least it can be validated with existing code.
Did you keep priorities, or did you remove them too?
Pardon me?
Did you keep priorities in the scheduler?
I did some kind of priority, but it's not configurable. And probably the most important criteria is to leave the existing scheduler alone. I don't want to go play in there. A lot of people rely on it. It's highly complex. It's somewhat fragile. As soon as someone touches something there, someone else somewhere will see regressions. So obviously trying to shrink that scheduler is suicide. So, slide 33. I did an experiment with an alternate scheduler. I started from BFS, which is already more simpler than the existing scheduler. At least I was able to wrap my brain around it. I stripped almost 2/3 of the existing code base. So I removed everything that I thought it was not essential. It has a single policy. Slide 34, please. So I ended up with a patch that will add only 3,000 lines. So it can be reviewed, it can be understood, and it at least compiles to, for example, my tiny config again. I was able to reduce the whole scheduler subsystem in half. And it still boots standard distributions. I was able to boot Fedora on top of that, do kernel compilation and so on. It works. Now, We're in Vegas. Bets are open if this is going to ever get into mainline. Slide 35. Another thing we can have a look at is the networking stack. That's another big part of the kernel. Of course, Internet of Things, there's the keyword internet in there. So we need network connectivity. What can we do with the existing stack? Maybe we can have something that keeps only the socket API alive. Let's get rid of all the routing, all the fancy features that are there to route packets at 10 gigabits per second with traffic control and everything. An IoT device probably doesn't need this. Of course, Samba won't work if we remove many features of the stack, but that's not the point. The point is probably to gather some data from sensors and just send them to the cloud. And once again, the idea is to remain compatible. Although we have a small subset of the current API, we still want to remain compatible with the full stack in order to test our application on the full stack and compare things. Maybe the ultimate solution will be to have only raw sockets and have a pass-through to hardware devices and having the IP stack in user space, highly optimized for the application using it. Slide 36. VFS. That's another part where we probably can save a lot of code. Once again, let's put ourselves in the mind of a very tiny device. There's only one task, no parallel lookups, no buffering, no nothing. Let's go to the bare minimum write and read support. So probably that we can have an alternate VFS layer that would bypass a lot of the fancy features that makes Linux so performant on servers. Maybe the ultimate solution, once again, would be to have only raw access to block devices and having file system support in user space, a bit like mTools does. So, slide 37. This is the vision that I have for this. Probably you've heard of Zephyr this week. I really appreciate what Zephyr is trying to achieve. Of course, we need to have something for very, very, very small systems. Let's say Zephyr, they say that it runs into 8 kilobytes of RAM. I don't pretend that Linux could ever do this. So there's a space for Zephyr, of course. But if we go to, let's say, 128 kilobytes of RAM, maybe that if we have a very small user space application that uses 10 system calls or so, and it does very simple memory allocation and has very small needs for networking, maybe we can have a setup that reuses all the existing Linux interfaces, all the APIs for user space and for drivers, and have a kernel which is highly optimized for the very minimum level of support that such an application may require. And the idea there is by doing so, we can have such user space application that would run either in your 128 kilobyte system or on your full-fledged workstation unchanged, because we're using the same interfaces that so many people on this planet are used to work with. And if you use the same application in most, and probably that you won't even have to recompile it. It will run on your full workstation with all the tools, the debugging tools that we have, the tracers, and so on. And the same can be applied for those different subsystems that we can work in the kernel. For example, if I take my scheduler experiment, I can swap between the regular scheduler and my tiny scheduler, test that everything works. I can debug it on any hardware. I can run it on any hardware, and it can be done by anyone, because it's not dependent on the hardware that you have. You might as well test your VFS replacement or bypass onto your workstation, and of course it won't scale as well, but it should just work. And by doing so, we benefit from the extensive hardware coverage that Linux already has. Now, this might work only if all those things are done upstream. I know that some people did work on those things. They were able to shrink the kernel very, very small, but those remained out of tree hacks, and they are just rotting there. So, that's it for me. Do you have questions?
Thanks, quick one. And I'm old enough to remember overlays as well. I think it's all great stuff, as you know. That's why I like you doing it. I think we need some hardware, as Arne's pointed out, to get this kind of doing these changes in the kernel will rot, and people cannot see the reason for them. But so I think we need some hardware. In my mind, that's probably a hardened core with FPGA around it and pretty small amounts of SRAM. What sort of size memory system would you need?
Well, like I said, my gut feeling is that we should aim for 128 kilobytes of available memory. Of course, we won't get there in the first try. Fortunately, there are development platforms from some Cortex-M implementation from ST, I think, which have 512 kilobytes of SRAM. So that would be probably the first goal. And once we are there, we just keep going down.
So I know that some people use upstream Linux in products with a couple of patches with 2 megabytes. So those are basically the same chips that you mentioned with half a megabyte, but they're using external SRAM. And that enables a couple of applications that you can't have with DRAM already, like because the power consumption is much lower than having DRAM. But the 512 kilobyte target, I think that's very interesting because it requires a number of changes that we don't have. Like some of the things you mentioned are easy enough to do that we can just try how much we have to do to get into that 512 kilobyte space and try to do something useful with them.
The tiny config kernel right now is down to 480K.
And that is text plus data, right? That's not just data. Because if you use execute in place, a lot of the memory would be in NOR flash, and only the data section and BSS would be required to live in an actual RAM.
It's probably it's the case in most of the time for very small microcontrollers. Most of the text executable is always in RAM or flash. So that's one thing. We need to revive the XYP support, but it's probably not that far.
Yes,
it used to work. It's just that nobody looked after it recently.
Yes, it doesn't work for any of the ARMv7 platforms because we lost the functionality with multi-platform support because it basically, the reason is if you have a kernel that runs on a lot of platforms, you can't rely on the kernel to run from a fixed physical address. And yeah, that just doesn't work. I think it basically works on the really small no-MMU targets that we would be using anyway. So the STM32 and the some of the others, I forget what they are.
And one thing I discussed with Arne yesterday or the day before, there is this trend in the silicon industry where you have SDRAM chips. The minimum size you can have is 32 megabytes. They're not producing smaller than that anymore. So if you don't want to use SDRAM because of power consumptions issues, you have to go with SRAM. And then SRAM, it's much more expensive. So there's a huge gap between 32 megabytes and a typical system with a few kilobytes of SRAM, or a few hundred of kilobytes of SRAM. So if we want to target that space, we really need to address this with new techniques like alternative subsystem and so on, because the 32 megabyte case is already well supported. Linux will run in those amount of memory pretty comfortably.
So I was just going to say the STM32 XIP, that was what you saw in running in the previous demo, just by chance.
Sorry, I didn't hear you.
At the demo in my presentation, which was before this, that was STM32 running XIP, execute and play, so it does work on upstream kernel. But you have to have a specific STM32 config. Yeah, like 8 megabytes.
Hi, Nicolas. So there is a big community around UC Linux, the micro Linux kernel. And I see that there's a lot of overlap between what you're trying to do and what UC Linux community will be interested in. Because it's basically it's targeted at the devices which are slightly more complex than IoT, but less complicated than a mobile system. Let's not say complicated, but in terms of its RAM sizes and everything. So should we not use the UC Linux community to make these changes, and should we not publish these proposals in that community so that we can leverage on a bigger developer base and do these things faster and probably in more mature way?
Well, there's one thing I didn't mention in those slides. Recently, I sent upstream some patches to be able to have the flat binary executable format usable on an MMU-equipped system. So if you're running your UC Linux distribution on your full-fledged ARM server, for example, it'll just work.
So maybe I didn't get the comment about UC Linux. Do you mean the actual UC Linux distribution, or do you mean Linux without MMU?
I mean the UC Linux community as a whole. There's a lot of community, there's a lot of engineers working on UC Linux support on different architectures. And to me, it sounds like the work that Nicolas is doing has a lot of overlap in terms of the end goals. May not be the methods, but in terms of end goals, what the UC Linux community would want to achieve.
So as far as I know, UC Linux is still on Linux 2.2 for most of the no MMU targets in ARM. So they basically abandoned ARM for going to newer kernels. I'm not sure, and I don't think that a lot of people are still actually using UC Linux. It's what most people are doing is they use an upstream kernel or a kernel from some company that uses no MMU. And what do you mean, just the UC Linux, like the user space tools with UC libc? And I still don't get what you mean with the UC Linux community.
basically, the idea is that to publish this proposal to a bigger set of people, a larger set of people. Could be user Linux community, could be the mainline community, so that we can thrash out the details of the designs, thrash out the different possibilities. Maybe we can come up with some newer things to optimize the RAM uses. And so eventually when you reduce the RAM size or RAM usage, you are also improving the performance in terms of cache optimizations and everything. So I would believe that it will have a lot more acceptance in bigger set of
I think you were next.
So obviously in the mainline kernel, there's been a lot of work over the years with tickless work and to make sure the CPU idle is really efficient. So with your nano scheduler, do we still get the ability to be really efficient with power?
I didn't have a close look at the power implication of those things. Probably that if your application is so simple, if you have only one task and the task goes idle, it should be pretty obvious what you need to do to save power then. The tickless kernel and so on, it's highly optimized for generic workloads. So if you control the environment of what you're running, maybe that the idle function in your kernel could be highly optimized for your purposes. So I don't think that in really, really small system, getting the best power possible, best power saving possible is a huge issue.
The other thing that's happening right now, that there's very active work going on, is to get real-time, the preempt RT patches upstream into the real-time Linux kernel. One of these domains for tiny kernels is obviously going to need real-time performance. To what extent have you been thinking about making sure that we can keep the tiny kernel with real-time capabilities?
The smaller the kernel is, the easiest it will be to get it real-time. Because then you don't have to cater for all the different subsystems and everything going in parallel and so on. So in theory, if you look at the existing small RTOS, they are real-time and their scheduler are very, very simple. So in theory, if we go with this idea of having a very small scheduler and small amount of tasks, it should be easier, I think, to have real-time performances from a tiny kernel than it is from a regular kernel. Of course, it might not have many relationship with the existing real-time patch set, though.
I have two comments to make. Number one, when you were, first of all, I appreciate your effort in trying to reduce memory, and you hacked away and removed many things. Have you thought about or talked to any of the SRAM vendors to get an idea about 2 or 3 years from now, what would be the minimal amount of SRAM that would be there, so that you have a goal when you try to fit your kernel into that? That I think is worthwhile looking at. That's an observation I'm making. And one other thing that, the second point was, in your slides, you said that there is no need for this IoT device to have a router on it. I mean, obviously, I agree with that, but I don't think you can assume that it will not route any of the packets to a neighboring IoT device. I think that assumption might not be valid.
Well, your IoT device is likely to be a client in your network. You're not going to use it as a router. So it won't have to forward packets. That's what I meant.
I don't know whether that is a valid assumption or not, because in machine-to-machine communication, I've seen applications where they do want to, if they run into a traffic jam on one route, they still want to use these IoT devices to be routing packets.
Yeah,
So,
well,
yeah.
if you do have a mesh network or things like that, probably it will be implemented into your stack. And if you have if you already have a stack that does this on another operating system, probably you could just reuse the same code in a Linux-based system, and it wouldn't be any bigger for that.
Yeah. The other idea is, like, this is not to make everything small, to make everything configurable. And if you need routing, then you turn on the routing again, and you have it. It's still there. You can turn off the routing and still have turn off the scheduler and turn off the memory allocator and all that. And for your other question, for the SRAM, this is the comments were about the integrated SRAM on chips, and there will always be the whole range. You will have microcontrollers with 1 kilobyte of SRAM and 16 kilobytes or 1 megabyte. We will always have the whole space. The question is more, which of these devices are we targeting? Are we only targeting the ones with 2 megabytes of SRAM on chip, which are very few, or do we go to 512 kilobytes or below 512 kilobytes?
I would like to make some general comments. So I remember a similar session a year or two ago, and in line was maybe people should look for something else but Linux if they want like low RAM usage, low kernel size. And the message was heard. Linux Foundation now has Zephyr system. Google recently announced Fuchsia project. And I'm happy that mindset is changing, and there is now thinking maybe Linux should go there actually to the small size. So I'm very happy to hear it. Maybe Linaro should do 96 board project with small enough RAM, but to be able to be used for such projects to validate them.
So was it a question or a comment? I didn't get it all. Okay. So I suppose that we're done. So thank you very much.